So we get the answers going here. Boom. Okay, take a look at these. These are the answers to the sig fig questions that I wanted you guys to take a look at yesterday. Are there any comments, questions, concerns? Is there anything anyone on there would like me to do? Sig figs isn't overly complicated. You just need to do enough practice to get the rules locked in. And those of you who are doing double duty in physics and chem, I think have had ample opportunity to do that. If you're only taking one, obviously physics 11, if you'd like more practice, I can get you more practice, but this is what sig figs, sig figs looks like. Lots of these, when we start getting into the meat and potatoes of physics 11, the answer keys I give you to the homework questions that I assign, some of them will be in scientific notation for exactly this reason. Like yesterday when we were doing this question, or I had 200.0 times 150 and I needed it to 2 sig figs, it'll be given to you as scientific notation because this is 2 sig figs, well this is 1 sig fig. So lots of times you're going to see that in your answer keys, so being comfortable with moving back and forth. Did I show you guys yesterday where I post your videos? The class videos to the lessons, did I show you that? Okay, I'm going to do that today. And I've already started recording, so all of these answers are going to be in there too. Here's the bottom chunk. So if you haven't finished it yet and you plan on finishing it on the weekend, you'll be able to access these videos and take a look at the stuff that's missing, or that you might be missing. Is there anything in there anyone wants me to do? Because you have questions about sig figs, or you got something different than I got and you feel like I may have made a mistake, or you feel like maybe you made a mistake and you don't know why, or it's Friday afternoon and you're really tired and we're just looking forward to the weekend. Okay, so there it is. If there are no questions about sig figs, let's talk about graphing, shall we? 3F, yes. Let us do 3F. Okay, let's zoom that sucker back in there. So questions like 3F. You guys are not my math nines, and so you are welcome to use a calculator for all of this stuff. I'm not going to say that you have to do it longhand or anything. If you do a question like F, what you're going to see is that 1001 divided by 40 is, did I screw that up in the answer key? I totally did. Whoops. I definitely did it backwards. Lovely. Okay, so we found a mistake in my key. Letter F, 1001 divided by 40. Wow, that was brutal. How did I do so poorly on that? It should be 25.025. Thank you, Lena, for asking the question. That's wrong. Meters cubed per kilosecond. It's weird. And we want to figure out how many sig figs we got around this thing too. This question this value has how many sig figs? This one has, it's got 1. There's no decimal there, so that 0 isn't significant. So this thing needs to be rounded to 1 sig fig. So this thing's got to be 30. Not 0.03 or whatever I had before. Be 30 meters cubed per kilosecond. Is that why you asked the question, Lena? Yeah, that was my bad. I don't know how I got what I got. Okay, were there any other mistakes you saw in there? Or was that the only one? You didn't see all the questions? Okay. All of the other ones, your answers and my answers were the same? No. There were other ones that were different? 92.45 divided by 1.01. I got 90. What? Oh, no, I had to multiply. I got 93.3745. So if it's 93.3745, and I've got 4 sig figs here and 3 sig figs here, rounding this one to 3 sig figs, yeah, would make that would turn that thing into a 4. That 7 would round that 3 up to a 4. Any other ones I should check? So far I'm 1 and 1. Again, never assume that you're the problem. We've already seen I can make mistakes. Okay. The rest are okay? And don't assume that you're the one making the mistake.
What about 3E?
3E. Oh, I converted it.
Different tops when you, because mine reads 2001 kilograms.
E?
Multiplied by 12.6.
3E?
No, 3.
2E. Oh, these just got relettered. Yeah, when I reformatted it to your guys's, they just, the A, B, C, D, E, F just got reordered. So your 2E is actually my 2F, 25,200. Yeah, they just got reordered. Properly, because this one doesn't have a letter D. It goes A, B, C, E, F, G. So that would have been D, E, and F. Yeah. D. That's my old copy. E and F. The new one should be formatted properly. Okay. We good? Rest are fine? Okay. Then let's review some graphing, shall we? Some of this stuff will be stuff you've seen in grade 10. Others of it will be slightly will be different. It will be a little bit pickier, perhaps, than some of the stuff you did in grade 10, and that's fine. I want to make sure that we're all on the same page with what the expectations are for graphing in a science like physics or chem. So, Unit 1, Introduction Graphing, Lesson 4, the linear relationship. What's a linear relationship? What is the general equation for a linear relationship? Who remembers? Yeah, here, Dave. It is a straight line. What's the equation? Yeah. Of a straight line. Gernot? Thank you, both of you. Y equals mx plus b. And let's look at all the different pieces. I don't care what order we go through this in. Someone tell me what one of these letters represents. Pick a letter, define it for us. Gernavin, is that a hand? It is. Gernavin, pick one. Y. What is Y? Not necessarily. The x-intercept? It is not necessarily. Each one of these has different pieces. So we're going to have that guy, we're going to have this guy, we're going to have that guy, and we're going to have this guy. Y, M, X, and B. What do these pieces represent? Diego, give me one. B represents the y-intercept. That letter B, whatever the value is in this equation, represents the y-intercept. And what that means is this is where the line hits the y-axis, and the coordinates of that point are always 0, comma, and then whatever this number is, b. So that whatever this b value is, it's the y-intercept, it's where the line hits the y-axis at that coordinate. Okay, I got 3 more letters. What do they represent? Y, M, and X.
MX is rise over run.
The M is the slope, yes. M is the slope. Slope is rise over run. How else can we represent the slope? You guys learned a bunch of ways to do this in grade 10. How do you do rise over run? Yes, your day. Yes, it's the change in y over the change in x. That triangle there means change in. It is the Greek letter delta. How do we calculate the change in y over the change in x? It's an expression that you would have been given at some point in the past, whenever Math 10 was for you. Yeah? y2 minus y1 over x2 minus x1. Absolutely. So those are all the different ways we talk about slope. Slope is rise over run, change in y over change in x, y2 minus y1 over x2 minus x1. And this is, I'll put it in here, between any two points. One of those points is going to be x1 comma y1, and the other point is going to be x2 comma y2. And that slope value is a measure of the steepness. Cool. So we've done N and we've done B. Now about y and x. What do those two represent? I'm going to grab a different color. Let's go to this one. Yeah, Lena. Which one? They're both variables. Y and x are both variables, but they are different kinds of variables. Which variable is the x? Okay, let's start throwing some stuff on the graph here. Yeah, it is x is the horizontal variable. When we're graphing this thing, I'm not going to go right down to the bottom corner. I'm just going to give us a little bit of space here. Let's throw that line there. I'm going to go 3 in. If you'd like a ruler, they are still on the front table. If you want to go freehand, by all means. I'm going to draw this here. I'll draw this here. So the x-axis is the horizontal one down here, which makes the y-axis vertical. What do we know about, or what variable? So sometimes you guys won't just graph y equals mx plus b. Sometimes you guys would have been expected to graph things with other variables. Things like, so in grade 9, I was having my grade 9s graph things like the number of rides you could go on an amusement park as it relates to the amount of money you have. Obviously, the more money you have, the more tickets you can buy, the more rides you can do at the amusement park. So where you would graph things like the amount of money you have and the number of rides you can ride go on, well, one goes on one axis and one goes on the other. There is a way to determine which one goes on which axis. Does anyone remember? It goes back to what we call these two variables. One of them starts with an I. Yeah, who said that? Your day. The x is what we call the independent variable. I always spell independent wrong. I think it's ENT. Independent variable. This is why I'm using different colors, because it's all getting crammed in there. X is the independent variable, which makes y the other one. The other one is called? If you're not independent, yeah. If you're not independent, you're dependent. This is the dependent variable. So the x1 is, the x variable represents the dependent variable, so the x-axis is where we graph the independent variable. I'll just go independ period, variable. I'll zoom this here, so it's easier to see. Y-axis then is going to be the depend, and I'll shorten that as well. Variable. And what makes a variable independent or dependent? Do you guys remember? Let's zoom out, slide back over here. I'm going to grab one more color and I'm going to cram something else into one of those spaces. What makes a variable independent or dependent? Who remembers? Stuff you've definitely supposed to have seen before. Lena, do you remember?
Well, I know that like time's usually on the x-axis.
Yeah, which makes time independent.
It's probably on like the compass, the y one.
Yes. Take it a step further. Gurnavan, I saw that hand over there. Because you can't change time. Time's going to change itself. Time's going to do whatever time is going to do, and then your dependent variable will change with respect to whatever your independent variable is already doing kind of on its own. If we go back to my example of the amount of money you have and the amount of rides you ride at the amusement park, which one of those is independent and which one of those is dependent? Does the amount of money you have depend on the rides you rode, or does the number of rides you can ride depend on the amount of money in your pocket? Do you show up to an amusement park and say, I'm going to ride 6 rides, and then the amount of money just magically shows up in your pocket? Or do you say, I have $10, what can I do? Generally, you show up with an amount of money. I mean, now in the world of debit cards and credit cards, that example kind of gets blown out of the window. Because you can say, I want as many rides as I want. I'll spend all of my money, which we generally don't do. But in the context of what I'm trying to get at is your independent variable, this one changes on its own, or you can set this. You're like, I'm going to show up to the P&E, I'm going to bring $50. Whatever I can do with $50 is whatever I can do. So the independent variable changes on its own, and the dependent variable changes with respect to the, and I'm going to call it IV because I'm out of space here. IV stands for independent variable. We're going back to your example with time. I mean, all sorts of examples with time, I mean, do depend kind of on how you decide to wrap your head around whatever the problem is. But let's say you're filling a pool, or you're, whatever, we're filling a pool. The volume of the pool depends on how long the pool's being filled for. So the amount of time you've been letting it go will dictate how much water is in the pool. You don't get to dictate the water in the pool. It's not like you say, okay, now there's 10 liters in here in this pool, so now it must be 3 o'clock. It's the other way around. At 3 o'clock, what time or how much water is in the pool? So time is, I'll say 98% of the time is going to be an independent variable, and whatever else you have is going to be dependent. That is not always true, but it is almost always true. Here, let's put something on this graph, and let's do some examples with some stuff. I want to put a dot there, so I'm up 1, 2, 3, 4. I want to put a dot there, and I'm just going to draw a line. I'm going to go that way. We've talked about a few things. We're talking about slope and y-intercept. Let's label those things on this graph, shall we? This point right here, just to give us a picture, that guy is the y-intercept. And it's going to have the coordinates y. In this case, it's going to be, I could put the value in there. 1, 2, 3, 4. 0, 4. It's wherever your line hits the y-axis. We can do a slope calculation for my line too. To do a calculation for the slope, if I just handed you a line, or if in Science or Math 10 rather, they just handed you a line to graph, you would pick 2 points that do what on the grid? like actually cross a grid corner, intercept the grid nicely. So find 2 points on the line you just drew. I'm going to find 2 points. I like, I don't know, that point, let's find a good point. That point there is a good one. Oh, and for me, that point there is a good one. Find 2 points on your grid, on your where your line actually hits the corner of some grids. Again, your line doesn't have to look exactly like mine. Find 2 points on there. And what I'm going to do is I'm going to connect them with a triangle. I'm going to call one of those point 1. My lower point is going to be point 1. I'm going to call the higher point point 2. And I'm going to do a slope calculation for mine. I want you to do a slope calculation for yours too. If we are going to say that each one of these tick marks represents 1, if my scale here is 1, 1, this becomes really easy to do. To figure out what my rise and run is, I just could count how many squares there are here. If my scale is 1, the run here, the run is horizontal. It's my change in x. My x goes over 1, 2, 3, 4. My rise goes up 1, 2, 3. So what I'm going to have here is I'm going to have a slope of 3 over 4. Write down whatever your slope is. Again, assuming here that the scale is 1 to 1. It won't always be, and then you have to actually put in the coordinates here. But if your scale is 1 and 1, you can just count. So we've got a slope, we've got a y-intercept, and so we can actually write down the equation of the line we just threw down by hand. The equation of that line is going to look like y equals, mine's going to be 3/4 x plus 4. That's what my equation is going to look like. I want you to write down what your equation is going to look like. The y-intercept, the coordinate of the y-intercept, goes where the b value is. The slope, whatever you calculated your rise and run to be, is your m value. Yeah, you've got to. See if it's okay. Okay, so we've said it already. We've kind of talked about it, and you guys, I mean, you're not giving me any sort of pushback, so I'm going to assume that we're doing okay with this. The walkthrough for the calculating of slope is right here. But you can see here there's actually something slightly different about what I've given you here. It says to find the slope of a straight line, choose 2 points, choose them as far apart as possible, and using only points on the line that are not data points. This last requirement's a little bit weird. I'll explain right now why it's there. Okay, slide down, take a look at this graph right here. So you guys drew one up for me in the top right. This one is one that I'm just going to hand to you. There is something different about this line than the previous line. What is weird about this line? What is, maybe not weird, but what is a little odd about this line? Here, Dave. The points are kind of scattered along, and our straight line doesn't necessarily go through all of them. Lena.
Yeah, like, I'm assuming the points that are already in the line, not the other way around.
Say that again.
They first put down the points and then.
Yeah, first we graphed the points, and then we drew the line. So this is the kind of thing that you guys are going to get when you collect data, or the example for this is there's a voltage and current that were measured. So you're collecting data about 2 variables that are related to each other somehow. The data looks like it's mostly straight, like it's trending to be linear. But if we drew a straight line through this, or we drew a line between every single one of these dots, it would be all sorts of jagged. We don't want to do that. So when you graph a line through a set of data, like you guys are going to do here in a little bit, we draw a particular kind of line. This line has a name. An arrow to this line. Does anyone know what we call a line that approximates data but doesn't actually necessarily go through all of our data points. There's a name for this. Anyone know? Wow, you guys are super quiet. That's okay. This is called a line of best fit. And we draw lines of best fit, and you guys are going to get a bunch of practice doing this because it's not necessarily super intuitive. A line of best fit gets drawn when the data looks like it should be a straight line, but for whatever reason it's not. Often the reason that the line isn't straight brings us back to that conversation yesterday we had about error. There's always going to be error inherent in measurements that you take. Maybe you looked at your measuring device a little bit early or a little bit late. Maybe something weird was going on within the instrument itself. Either way, this, for example, this point here looks a little odd. But all the rest of the points kind of follow that path. We use the line of best fit to approximate what we expect it to be. So I'm actually going to write that explanation up here. This is, make sure I actually fit it in there properly, a line that approximates the data. Or I'll say it this way, a line that approximates data that looks linear. The beauty of the natural world is that there are equations that govern all sorts of weird phenomena. And we know what those equations should look like. We've derived them. Our experience with the universe verifies that these are what things should look like. But when we take measurements, again, we make mistakes. Instruments aren't perfect. And so sometimes we get points that don't necessarily align with what we know they should align with. And so we use lines of best fit to match what the universe tells us the math should be and not the other way around. We call those lines of best fit. Or if the line's not straight, if it's curved, representing maybe a quadratic or a cubic function, we'll call them curves of best fit. And you guys are going to draw some of those for me too. Which reminds me, I have to go get the French curves back from Mr. Morrison. So we've got lines of best fit, don't totally go through the data. And so when I put this over here and I say, okay, when you find the slope, use only points on the line, not data points. We can go ahead and do that now. We want to make sure we're not using data points. Like, for example, this data point wouldn't make sense to use because it's not only is it not on the line, it's really not on the line. So we want to make sure we use points that are not data points, but that the line actually goes through. The ones that I picked earlier, I picked this guy right here. This is one of them that I think looks good. It looks like it goes through the grid. And I picked another one. Where's the other one? I like this guy right here. So we're going to do a slope calculation again, except this one's going to look a little different. The previous slope calculation we did, I told you to assume that the grid, everything went over by 1 and up by 1. But you can look at this one. Does everything go up by 1? Alexis is saying no. It's not. Everything's got its own scale here, right? In this case, every 1, 2, 3, 4, 5 lines is 0.1. So what does one of these things represent? Well, to figure out what one of these represents, you can take your scale and divide it by how many lines there are. So it goes from 0 to 0.1, and there's 1, 2, 3, 4, 5 divisions that do that. So to figure out what one of those represents, we're going to take 0.1 and we're going to divide it by 5. 0.1 divided by 5. Nope, that's not right. I got 0.02. So every one of those tick marks represents 0.02. And vertically, we've got a different scale that way. This one goes up 1, 2, 3, 4, 5 tick marks is 0.2. So we're going to take my 0.2 and we're going to divide that by 5. 1, 2, 3, 4, 5. 0.2 divided by 5, that's 0.04. And so this particular graph that's been handed to us has two different scales, one for the x, this way, and one for the y. And so when we actually go through and we figure out what our rise, this way, and our run is, we can't just count them up. We actually have to do the calculation using what these coordinates are. And so we can go through and we can plot what these coordinates end up being. If we take a look here, this point here is 0.1 is there, so this is going to be 0.12, 0.14, 0.16, 0.18 is this guy here. So the x coordinate is going to be 0.18. And the y coordinate is nice. The y coordinate actually lands at 0.4, so that's cool. And then up here, we can do the same thing. We want the x coordinate and the y coordinate. So the x coordinate for this guy is 0.3, 0.32, 0.34, 0.36, 0.36. Oh, and this one also lands nicely on the y-axis. That was convenient. It's going to be 0.8. And so now we can go through and calculate the slope for this thing. Except instead of using just the change in y over the change in x, we're actually going to go use that other formula. The slope equals y2 minus y1 over x2 minus x1. And we can use these values. It doesn't matter which one you call 0.1 and 0.2. For the sake of simplicity, I will almost always call the lower 1.1 and the higher 1.2. So then to plug this thing in, my y2 is 0.8. It's going to be 0.8 minus 0.4 over my x2 is the x coordinate of 0.2. So that's going to be 0.36 minus 0.18. So if you plug this thing into your calculator, what is the slope of this line going to be? Well, if you're going to punch it in all at once, make sure you use brackets properly. It's going to be 0.8 minus 0.4. I'm going to close that bracket. Divided by, I'm going to open another bracket, 0.36 minus 0.18. Close the bracket. And I get, what is that, 2.2 repeating? So if I've got a slope, but what does that slope actually mean? We're going to spend a lot of time in Physics 11 and again in Physics 12 actually looking at what this slope means. If we take a look at what we've got here, slope is a change in y over a change in x. What is my y variable? It's voltage. What's voltage measured in? What are the units for voltage? Think back to grade 9. This one's actually kind of easy. It's in the name. Voltage is measured in volts, yes. So on our graph, what we want to make sure we do when we graph is include the units as well as what the variable is. So voltage is measured in volts. Does anyone remember what current is measured in? Current is measured in amps. Very good. So if I have a rise over a run, my rise was volts, my run was amps. So this thing, 2.2 repeating, is 2.2 volts per amp. I want to put my units on there. And now we can actually go ahead and make our equation, which I'm going to do in this box over here to the left. It says at the top, determine the slope and y-intercept of the graph. We've done that already. Well, we've done the slope. We haven't done the y-intercept. We're going to write the equation that describes the graph. So when you're asked to write an equation that describes a graph, always and forever start with y equals mx plus b, and then fill the thing in. Because our data actually has variables that aren't x and y, when you create the equation, create the equation using whatever these variables actually are. Y is voltage, so we're going to actually put the word voltage in here. So the voltage is going to be equal to, M is our slope, we calculated that already, that's 2.2 repeating. X is current, so voltage is equal to 2.2 times the current plus what? How do I find the y-intercept? What has this graph not done? Does this line of best fit touch the y-axis? You guys are really quiet. This is how we're going to be all semester. That'll be sad. Be louder. Somebody. If I want the line of best fit to hit the y-axis, what do I have to do? Yeah, grab a ruler and extend it. So for me, what that's going to look like, I'm going to turn it sideways so I can do it a little easier. What that's going to look like for me is I want to make sure I can get all of, or as much of my data done properly. It looks pretty good to me. Question is, what is that point? That point is not 0. It would be really great if it was, because if there is no current, there shouldn't be any voltage. But clearly we've got some error in our line of best fit. That's okay. What if you had to approximate that y value, what would you say it is? Yeah, here, Dave. Yeah, it looks about halfway, right? I think that's a totally acceptable approximation. There's no reason why we can't call that 0.02. And so what that means is our equation is going to be voltage is equal to 2.2 repeating times the current plus 0.02. This is the equation of the line of best fit. And when you graph something like this value right here, which color do I want to use? Let's use blue. This value right here in the equation actually represents something pretty awesome. What this thing represents is, like, conceptually, the universe we know, you did it in grade 9, perhaps you'll do it again later as you do more physics, we know that there's a clean relationship between voltage and current. Does anyone remember what the relationship between voltage and current is? V is supposed to equal what? I times R. You were told this back in grade 9, that this is the way it works. But now if we go back and look at our data, V is voltage, current is I, so what does this value here represent? R, and R is? Resistance. So this value right here is the resistance in the circuit that this data was recorded from. And what does this represent? There is no plus anything in this case. So what does that represent? It represents a concept we've already discussed this semester. Actually, the last 2 days we've discussed this. It might have even been yesterday. What does this plus 0.02 represent? 5 letters starts with E. Error. So sometimes your error is going to come out of your graph all on its own. And it's actually, and I can't stress this enough, it's really nice when you've got error. Because it gives us something to point to. We say, so effectively what this is going to mean is that voltage is equal to 2.2 repeating times the current plus or minus 0.02 volts. It's a really convenient thing that pops out here. But this is what it looks like to actually work with real data. Questions about anything I've done here? There is one thing that this graph that I provided you is missing. When you guys graph your own data, lots of this stuff is modeled for you, and it's actually going to be on the handout on the next page that I'm going to talk through. Lots of wonderful things are here. Don't flip ahead yet. And it's not the next page, it's the next page. We've got voltage and current labeled here. Our variables are labeled. We added in, or I added in, I hope you did too, I added in the units on those variables. We've got our points, we've got our line of best fit. I did my slope calculation right on the graph. I've got a y-intercept labeled. This graph is just missing one thing. If you graph things in Science 10, if you had me, you did. We graph things in the chemistry unit. There is one thing that every graph should have, especially when there's context like voltage and current in here. Yeah? There should be a title. The one thing that's not on this graph is a title. And the title of any graph always should be nice and clean. It's almost always only two things. It's your independent variable. Actually, it's your dependent variable first. Voltage versus current. Your dependent variable versus your independent variable. Every graph needs a title. So it's the only thing this one was missing. So, I want you to flip the page twice. Well, flip the page once. We're going to come back to this. These are just some simple slope calculations. I want you to do these for homework. Just to review slope calculations, these should not take you very long. I want you to flip the page. I'm going to talk through this, and then I'm going to give you the rest of the things that I want you to do. Okay, here we go. So, graphing data. When you guys graph your own data. So a common process in science is to determine the relationship between two variables. You guys are going to do this. To do this, we manipulate one variable to see how it affects another while keeping all other variables constant. You guys are going to do this in a few different labs. And a good way to analyze these relationships is to always plot, I shouldn't say plat, plot a graph. And so this page just walks you through stuff that I've already said. Every graph must have a title. It's usually a statement of the dependent variable versus the independent variable. Sometimes it gets a little bit more specific. You could say it's dependent versus independent for whatever your object is. So you guys are going to, probably next week, maybe the end of next week or the beginning of the week after, you guys are going to race two cars. There's going to be a blue car and there's going to be a red car. And you're going to graph the relationship between the distance traveled for each car and the time it takes each car to move. So you might say that your graph is distance versus time for my red car, or distance versus time for my blue car, or distance versus time for two cars. What is often that gets included in the title, but dependent versus independent is at the bare minimum what you got to have. Your axes need to be labeled with your independent and your dependent variable. And you've got to include units. Don't just say distance. Say what the distance is measured in. Meters, or centimeters, or millimeters, kilometers, whatever the distance is, include the units. Scales, you've got to choose a good scale. Choose a scale that makes the graph as large as possible on your page, but use reasonable increments. When I say as large as possible, when you guys are going to do graphing for me, I want you to use at least, so at the bare minimum, half the graph I provide. So you need to pick a scale that allows you to use at least half the graph. I don't want you to cram something into a bottom corner. I want you to make these things big so that we can actually analyze them. It's so important. You wrote it down, I hope, and it's the next bullet point. Students forget this all the time. Use at least half the graph. Good examples of good scales. What kinds of values make good scales? Or maybe let's go the other way. What numbers make terrible scales? What's the simplest scale you could possibly do for a graph?
160.
Yeah, ones. Ones make good. That's not 1 second, that's plurals. Ones. Going up by ones is often a great way to do it. Halves. Halves aren't terrible. Evens. Evens are usually good, but you want to avoid some evens.
What are evens?
2, 4, 6, 8, 10, 12, 14, 16, 18, 20. But there's some evens you want to avoid. Generally speaking, we want to avoid multiples of odd numbers. So not all even numbers are good. Some even numbers are very bad. Yeah? Yeah. You can go to the bathroom if you can tell me an example of an odd or of an even number that's a multiple of an odd number.
14 plus 14.
Yep. 14 is an example of an even number you want to avoid like the plague, because 7s are terrible. And sometimes you're going to need to go in the middle. You go to the bathroom, by all means. You're going to need like a half point. And so if you're going up by 14s, half of that is 7, half of 7 is 3.5, and now all of a sudden your work is gross. The simplest example here they could have given us was 6. Avoid 6s like crazy, because half of 6 is 3, and now you want to avoid 3s. You want to pick even numbers, but avoiding multiples of odds. 5s are okay. 10s are okay. Generally speaking, though, you want to keep it to things like 2s and 4s, multiples of those. But you're going to have a lot of freedom to pick your own scales. Data points, you're going to need to include those. Data points should be placed as accurately as possible on the graph paper. Take the time, take the care to do that well. And then you're going to graph a best curve or a best line. Data points do not usually line up perfectly due to experimental errors. Draw the line or curve that comes as close as possible to as many points as possible, and you really only get comfortable doing this doing a bunch of examples of this. If the trend line is straight, use a ruler. If not, we have other tools. If not, a French curve. And we've got these. I'm going to go grab, Mr. Morrison and I share them because we both teach physics. I'm going to go grab these from his class. He taught Physics 11 last year. French curves they're like rulers, but they're curved pieces of plastic. And each curve on them represents a different mathematical function. So one curve will be parabolic, one curve will be exponential, one will be logarithmic, another one might be a cubic. And so these are kind of swirly little pieces of plastic. I'm going to go get them from him momentarily. As soon as I get you guys working, I'm going to go grab them, and I'll show you what I mean. Do not, underline that word not, just connect dots, ever. You can't analyze data if you just connect the dots. You'll get this jagged-looking monstrosity. Don't do that. And so I've got a couple examples. I'm not going to do all of them because I want you to play with some of them. Yeah. The only way we're going to get a handle on this is to practice them. So I'm going to do this first one, and then I'm going to free you to play with it. Here's what I mean. So we've got data here. We've got depth underwater, and we've got pressure. The pressure is measured in something called an atmosphere. So this is multiples of atmospheric pressure. What you guys are experiencing right now at sea level is 1 atmosphere. As you go underwater, hands up if you've ever dove underwater and you can feel the pressure on your ears. You ever experienced this? If you have not experienced this, go learn to swim. As you go deeper, you can feel the pressure starting to build, and so there's a relationship between your depth. So 5 meters underwater is 15 feet. 5 meters is probably even deeper than the deep end of the wave pool, I think. The deep end might only be 3 meters at the wave pool. But 5 meters is 1.5 atmospheres. You can feel the effects of the pressure building pretty quickly. And we want to graph this to find the relationship between pressure versus the depth of the water. So let's do that. I've got a grid here. We've already got x and y axes. We're going to put the depth underwater in meters, because that's the thing that we can control. And the pressure in atmospheres is the thing that changes as a result. We can title this thing, I'm just going to title it pressure versus depth. And now now we're going to have to put down a scale, and that scale is going to reflect the values that we have here. So the depth underwater goes from 0 to 25 meters, and the pressure goes from 1 atmosphere to 3.5. So it should be pretty obvious that we're going to need different scales for these two different pieces of the graph. Can someone give me a good example for what they think a scale might be for depth underwater? Going up by 5s? Yeah, because our data goes up by 5s really nicely. 5, 10, 15, 20, 25. Do you want to call every line 5, or do you want to call every 2 lines 5, or what do you want to do?
Every line.
Okay. If we go every line 5, it's going to take us 5, 10, 15, 20, 25. That's exactly halfway down the graph. That's okay. 5, 10, 15, 20, 25. We would have had enough room to go every 2 lines as 5, but Liam has chosen what Liam has chosen, and it covers at least half the graph, so we're good. Let's go vertically. It starts at, well, 1, which is interesting, and goes up to 3.5. So what should we scale this thing? If we want to use at least half of the available graph. 0.5 is something that would make sense. 0.5, 1, 1.52, 2.5, 3, 3.5, 4. It might be useful to have 4.5 and 5 on there, so let's go 4.5 and 5. And now we want to be real careful to actually graph these things properly. The first point is 0 and 1. That's really nice. 0, 1, that's really easy to put right on the grid. The next one's going to be 5 and 1.5, also really nice and easy to put on the grid. Then we've got 10 and 1.9. So where's 1.9 going to be on the Y scale here? You better not put it right at 2, because that doesn't make any sense. Halfway up would be 0.75, because halfway between 1.5 and 2 would be 1.75. So maybe there-ish. Maybe that's 1.9. Uh, 15 is going to be 2.4. Well, it's got to be obviously lower than 2.5. 20 is going to be 2.9, so just under 3. And 25 is going to be right up at 3.5. So if you don't have a ruler, I would encourage you to grab one from the front. I'm also going to grab one from the front because all of my rulers are up there. And when you're grabbing a ruler, it doesn't, for lines of best fit, I'll say it this way, avoid these little plastic ones. We don't care that we're not actually measuring stuff, you're just using it as a straight edge. So make sure your ruler is clear, because then we can get an idea of what this thing's going to look like. We want a line of best fit. And a line of best fit is going to approximate as much data as humanly possible. So here's kind of the process for going through and talking about, even to yourself, what a line of best fit could look like. If I want these to include these three middle points, because they go up kind of nicely, there's a 1.9, a 2.4, and a 2.9 there. So they're all just below the same level. If I do that, what I'm going to do is I'm going to miss these 3 points up here. I'm going to miss 3.5, I'm going to miss 1.5, and I'm going to miss 1 here. If I go here and I want to draw a straight line through those 3 points, you can see on the ruler, these 1, 2, 3 points are going to be below the line that I draw. Are there points that are more important than other points?
Starting point?
In this case, not always your starting point. Sometimes your starting point. Is this starting point going to be the most important? Probably. But where does your starting point need to be if you're going to be right at 1 atmosphere? See, these are the kinds of questions you have to ask yourself. Where is it going to be exactly 1 atmosphere? 0 meters. So at sea level. Are we in a pool? Are we in the ocean? Question doesn't say. If we're at the ocean, this point right here, we know that to be true. Right at the surface of the water, atmosphere is going to be 1. So let's assume we're at the ocean. To make our life easier, we are at the ocean. If you're at Cultus Lake, is the depth, if you are 0 meters below the water, are you going to be at 1 atmosphere exactly? No, because you have altitude. As you increase in altitude, you decrease atmospheric pressure because there's not as much atmosphere above you. Some atmosphere is below you. So you're going to have different pressures. At the ocean, this is a very good point. So much so that I would argue that we could make sure that we're right through it. That might be the only point that we could say on here for sure needs to be there, because any one of these other points as we descend beneath the water, how do we know when we are exactly at a specific depth? We don't necessarily. There could be error in even down to the millimeter, right? So we know, assuming we're at the ocean, that first point's probably going to be bang on, but these other 1, 2, 3, 4, 5 points might not be. So what I'm going to do is I'm going to draw a line that does its best to kind of split the difference between these 2 points and these 3 points. I'm going to weight those 3 points perhaps a little heavier because there's 3 of them versus these top 2. And so my line of best fit is going to look like this. I'm going to send it right through this first point because we have pretty strong confidence in the data recorded at that point. And my line of best fit splits the difference between these points above and these 3 points below. And so now to take the slope of these things, unfortunately with the data that we have, there aren't a lot of points that are right through the grid that we've got. There's really only 1. We do want to avoid, and I did say this already, we want to avoid using data points as much as possible, but in this case we can't. We are confident in this value with such certainty that I am in fact going to use it to calculate the slope. And then we've got to pick another one. What's the next one that we could go? I don't know. Even if I extended my point, I'm still not going to hit anything. So are there even any nice like halfway points? No. So this isn't a great situation we've cooked for ourselves. But we've got to use it because that's what we've got available to us. Let's go here. Let's make an argument for that point there, shall we? That point there is going to be down here at 30. And if we have to follow that line, see, this is the problem with going up by halves. If we have to follow that line, what could we say that value is? Well, that's 3.5 there, that's 4 there. How far along there are we? We are 0.1, 2, 3, 4, 5. I don't even know. That's not even a full centimeter. What is the distance there? The distance there is, oh, that's terrible. So we have to ballpark this as best we can. The coordinates of this point are nice and easy. They are 0, 1. What are the coordinates of that point there? Well, they're going to be 30, something. If you had to ballpark that, what would you call it? Someone give me a guess. What are you comfortable calling that point? 3.9? Okay, let's call it 3.9. And if that's true, let's crank out a slope calculation. Slope equals, so I'm going to call this 0.2, I'll call that 0.1. So we're going to go y2 is 3.9 minus 1 over x2 is going to be 30 minus 0. So what do we calculate the slope to be? 2.9, or 3.9 minus 1 is 2.9. 2.9 over 30 is 0.096 repeating. So there's our slope. We can plug in what this means. This is atmospheres per meter. If we were to stop and think about what we just measured, it might actually stop, well, we might actually want to stop and think about, does it make sense to round this to kind of a cleaner value? Does it make sense that every meter of depth goes up by 0.096 atmospheres? Or does it make more sense that this value could or probably should actually be rounded to 0.1 atmospheres per meter, based on how the world works? You could make a reasonable argument for making this rounding, especially if you go and look at the sig figs here. How many significant figures are in this calculation? Well, there's 2 sig figs here. There's when you're adding, you don't care about sig figs, you care about decimal points. This one has 1 decimal point. This one has no decimal points. So when you do the subtraction here, you need to round this to something that has no decimal points. So 3.9 minus 1 is 2.9. That would round to 3. And then 3 divided by 30, each one of those has 1 sig fig. 3 over 30 is 0.1. So if we bring in the sig figs that I wanted you guys to do yesterday, it actually makes a lot of sense to round this thing to 0.1 atmospheres per meter. And so now we can actually go through and make a calculation for this. Not a calculation, an equation for this. The equation for this is going to be, if I start with y equals mx plus b, y represents pressure, is going to equal the slope, which is 0.1 times your depth, plus 1 atmosphere. So there's our calculation. In this case, that plus 1 doesn't represent error. That plus 1 represents that at the surface, you've already got 1 atmosphere stacked on top of you. Questions about anything I did there? Okay. If there are no questions, then what I'm going to do now is I'm going to free you to play with some of this stuff, because the only way you're going to get a handle on, especially these lines of best fit, is to do a bunch of this stuff on your own. I want you to try. So first of all, I want you to do this as part of your homework. And then I want you to try, there's a whole ton of stuff here, but you're not going to do all of it. I want you guys to start with just some more of these examples here. Example 2, example 3, especially with the time you got left. You only got about 15 minutes left. Sorry, that's what I meant. I want you guys to do this. I want you to try this. I'll walk around and I'll help where needed. I want you to do 3A for sure. So I want you to do B, that guy and that guy for sure. A versus B, graph that table there. You do not need to do, yeah, you know what, let's do 3B as well. Let's call that there. That's what I'll give you for today. I'll walk around and help where needed. And you could theoretically get that done in the next 15 minutes and have no homework over the weekend, so that would be great for you. Okay, on your market, set giver. It should be 3 graphs. Example 2, example 2, example 3A, and 3B. So there's 3 graphs there, and then the previous page that I wanted you to do.